it really happened, so he gets kicked out. And then one other guy said, you must be devastated that this happened to you. And he said, no, I just imagine that my skull is myself and the flesh around me is my house, so I'm always at home. And then it's a very sad story. So if you don't have a neighbor, then just imagine that's totally fine. Just talk to your skeleton or so. So, we're good to go. Talk of today is called Why Rust. So I could have named it Rust, Introduction to Rust. But to be honest, Rust is yet another programming language. And so you, yourself, might ask yourself, oh, why should I learn Rust? Why not learn, I don't know, Swift or lol code? Why learn Rust? Because Rust brings something new to the table that was not there before. And this has changed the game for all the other languages that will come. And this is why I named it Why Rust, not just Rust. So raise your hands if you ever played around with Rust already. So somebody? Okay. You are contributing, so some of you have already a cargo package on the cargo repository. Yeah, you're the dangerous one then, for the ugly questions in the end. This is going to be a very lightweight talk. I don't want to make this a big thing. I just want to show you some small features, some code, and then give you some pointers on where you can go from there. The most important part is, for me, the community, because you can go back and learn so many new things from those people. Speaking of the community, it's very important for me because I come from a very different angle of programming. So I work at Trivago. I live in Düsseldorf. I'm in the website performance team. So what I do on a day-to-day basis is look at profiling code, optimizing code, and so on. But actually, I'm from a PHP and Python kind of thing. And Rust, for me, is eye-opening in a way that many other languages tried, but failed for me. And I do like hot chocolate. So let's chat about that. There's one slide that will come up next. A friend of mine said, don't put up this slide. It's super confusing and it's intimidating. But in reality, this is how I feel about the other systems programming languages. Yeah, just sometimes they are scary, you know? You work with them. A lot of people maybe use them at university. You say, okay, I know this. Okay, it works, perfect. You write a simple application, you run it segfault. You say, what the hell? And there's a lot of things you need to learn to really, really use those languages. If you want to be proficient in C++, it takes just a lot of effort. And even then, bad things can happen. There's even so many bad things that this thing, for example, even has its own logo. So that's the official logo of Heartbleed now. They created a logo for that particular bug. And there's some discussion going around how this happened, but it can happen to the best. Even if you're the best C++ programmer in the world, you make mistakes because you're just human. And it's always better to have some external balance to check you on your constraints, saying, okay, this is fine in 99.9% of the cases, but you didn't look at the remaining percentage. And that's where Rust comes in. If you want to build something like OpenSSL or any graphics tool yourself, you need to put in a lot of effort. And if you start from scratch, it's very, very hard. Systems programming itself is very hard. You have manual memory management, at least in C and C++. You have custom error handling that you need to do. There's things like static typing that you know, but maybe you haven't used it since university or not used it at all. Because in scripting languages, you have dynamic typing, for example. You don't need to care about your types. What is a type? This is something that is abstracted away from you. You need to care about compiling your code, so not interpreting, not running it on your local machine just by calling a program. No, it needs to be compiled as a binary, and it needs to be compiled for your platform. So you cannot run the same binary on Windows and Linux. It's not possible. And things like that, and on and so on and so on. So why even do systems programming then, if it's so hard? Well, because it enables you to go at a level where you cannot go with, say, scripting languages like Python or so. There's just a boundary that you cannot cross. And you might say, maybe now I need to use C++, but then again, I need to put in so much effort to make this really work. And you say, I'm stuck. I want to do systems level programming, not only web development. I want to do real applications. I want to do firmware. I want to write a scheduler, maybe some operating system even, some emulator. But you cannot do this, at least not very performant, and there's some constraints. It feels a bit like a cargo cult. Sometimes you have those dynamic languages, you say, wow, cool, it's easy to start. But then you kind of don't have the control over all abstractions to go to a very low level. But Rust tries to change that. It's also a systems language. So just some facts about the language. It was created by Graydon Hoare, who worked at Mozilla at the time. And he was doing this just for fun, just to say, oh, can I make this work? And then after a couple of years, as a side project, Mozilla picked it up and said, wow, that's a pretty neat idea that you had right there, because we have so many bugs in our Gecko engine, for example, and so many bugs in WebKit, and so many bugs in the rendering engines in other browsers. It is just a mess to maintain all that. And so they picked it up, they funded it, people came in, Graydon left, there's a couple other people that came in, like Steve Klapnik, PC Walton. Those guys, they were very, very profound. And so the first version was in 2010, but then everything from there, first major version was last year. But since then, we went from 1.0 to 1.8. And the core hasn't changed much. So that's a proof that they are onto something. It's just stability that improved. Compared to C++ and C, it tries to remove the challenging part from systems programming. Systems programming is challenging. And okay, here's a workaround, but that doesn't work for systems programming. If you run it and you made a mistake, then it will crash. But it can be fun. And what are some ways this can be fun? Rust provides the right abstractions. So it gives you some tools that you can use without any cost. And the compiler will optimize it away from you, but you can write code in Rust, like in Python, on a very, very high level. Who's a Python developer here? Ruby? PHP? Don't be shy. It allows you to make mistakes. It's totally fine if you come from a dynamic background. No problem. What? I heard Snoop Dogg and I said, that's not a programming language. Yeah, I know. I've heard of this obscure language called Smalltalk before. But to bridge the gap from a dynamic perspective and a systems level, the community comes in. Very helpful people on IRC, on the forums that just pick you up and say, okay, it's cool, you can use it. All of those languages, they follow two areas, I would say. You can make it fast or you can make it easy. But both of them combined, that's very tricky. In PHP, you start on a very high level. It is easy to get started. It's very hard to make it fast. And you go down to Python. Maybe some people already used Golang. Then there's Rust, and then there's C. That's just where we are in the kind of area. And I would even say Rust is now challenging C when it comes to speed, because a lot of checks, as you will see, they can be avoided just by safety of the language itself. I like the term high level on bare metal. High level language, but if you really need it, you can drill down to the very bottom, like in C++, but with more safety. And if you ever want to write your own emulator or programming language, Rust might be something that you want to look into. If you, for example, I'm writing a CPU emulator, and it's very helpful to have this those little checks and guarantees. I never touched something like this before because it's just out of my scope, I thought. It's not. Also finance. We trust a lot of our of the things we own. We trust some big corporations, like money. We trust them to some finance corporation. And in reality, they use maybe a C or COBOL or something, or Fortran, and all of them, they are kind of error-prone. And you don't want memory leaks, and you want to avoid things like segfaults in that area. So also maybe space travel. Imagine SpaceX or so. You want to build reliable software, or Tesla. You want to have a system steering your car that does not segfault maybe on the highway. So let's look at some Rust code. And I was thinking a long time about what I want to show. And I want to make it simple for you so that you kind of can relate to the language. The syntax might be similar to other languages, but the semantics are not, and that's a big difference. The semantics are more powerful than in other languages. But just to get started, if you want to write a simple address book, for example, you might have a struct called person. A struct is just like a C struct, and you can also create structs in C++ with a name and some values. So let's say you have a first name, a last name, and maybe you have an age. And then you can implement methods or functions on this struct. And that's where the impulse statement comes in. So for example, by convention, you have a new function, and this new function, it will return a new instance of your person. So whatever is last in your function will be returned. So for example, here, the last thing and the only thing in the function is person itself, and this is what we will return from that. As you can see also in the return statement here. And then, if you want to use it, you can, for example, create a couple persons from that in your address book, say. You can create a vector like in C++, and then you can create some instances of your persons. Now there's one thing that is different from, let's say, a scripting language. And that's this one. You have string from Austin. You might say Austin is already a string, and Powers is already a string. So why convert it to something like a string? Well, in systems languages, you need to know the difference between a stack and a heap. So a stack is something local to your function. And if you run out of the scope of the function, then this memory will be freed. But on a heap, this is something more dynamic, that objects will be created at runtime there, and they will be available until you remove them again from the heap. So you have static memory and dynamic memory, if you like. And this one, this is on the stack. So this is just a string slice, as we call it in Rust. And you create an object on the heap with this constructor here. And what it will do is, it will copy this one at runtime to your heap, and then it's available, and it can be used in the person struct here. So the person now has a copy of this string. And it also has an integer that is also available. And you can push this person now to our vector. And you can, let's say, push multiple persons to the vector. And if you're done, you can iterate over that. So you iterate over a vector which just contains our persons. And for each person, you could, for example, match on a certain attribute of it. Say, match on the person age. And you say, if it's from 0 to 18, it's a teenager, then from maybe 18, old enough to go to war, and then everything else is too old. So very simple matching of your struct fields here, and saying, okay, if this, then do this. A very powerful metaphor that comes from functional programming. And this is some abstraction that is available in C++, but not with that safety. So you can, for example, not forget a case with a match statement. You always need to cover every case to make sure that you don't ignore an error or so. For example, here, there's all the cases that it can appear. So it can only be from 0 to 18, it can be 18, or it can be anything else. So anything else can also be all other numbers. And if you want to make this parallel, for example, it's very easy in Rust to make things parallel. You can iterate over that with a parallel iterator and make that work. Yeah? The integer? I don't get the question, to be honest. So the number, or? Okay. So this is known at compile time. This is a fixed static string that you can say will never change in the whole time when your program is running. You can compare this. You have this in, let's say, the data block of your program in the binary, and you compare this to your dynamic element, to your dynamic string that you have on the heap. Here? Yeah, but here you're using this to allocate a new object dynamically. Okay, this one is known, but still it needs to allocate this person object to put it into the vector after that, for example. So this part is known at compile time. But also, this is going a bit into too much detail right now. Maybe we can discuss it a little bit later, because we don't have too much time. But what you mentioned is very important. There's a difference between a stack and a heap, and things like this can bite you in the beginning a little bit. But it's just a bit advanced right now. Apart from that, I like other languages as well. What I like about PHP is the package management system, and also the community. They have a strong community, and Composer is pretty nice. In Python, I like the syntax and the libraries. In Go, I like tooling, documentation, concurrency, in some way at least. In C, I like the speed and the low overhead. And in Rust, I like everything of that. So there is an awesome package manager. There is, I wouldn't say awesome syntax, but it's okay. But there's definitely awesome documentation, and there's speed. And there's also things that I don't like about those other languages. So for example, in PHP, I don't like the syntax that much, and legacy functions, what comes first, the haystack or the needle? And in Python, you don't have that awesome of a package manager, at least if you want to push something out to the public and open source. And 2 versus 3 is a hell. So the community is right now a bit split into those 2 versions. In Go, I don't like the error handling. And the package manager is not super sophisticated. You didn't have vendors for a long time, so no versions on your packages, for example. All of them were globally installed. This is fixed now, but still. No generics. Syntax also is a bit weird. And in C, I really miss the package manager sometimes. And also, of course, safety. But there's also a lot of things that Rust is not good at. So the syntax, you might say, is weird. Fighting with the borrow checker, this is also what you mentioned before. You need to get used to this a little bit. You have some missing packages because it's just a very young language, and probably a lot more. There's a couple things about system programming languages that you can categorize. So let's say, let's start with type safety. So that means you have some block of data somewhere in memory, and yeah, C allows you to interpret it as whatever you want. You could say, okay, this is now a string, and it will be interpreted as a string. You can say, okay, this is, I don't know, this is my name, but in reality it's the money on my bank account, and it will just say, okay, money on your bank account. It's a string. In C++ you have the same problem. In Go it's a bit better. There's type safety. So what I mean with that is at compile time you know what happens, what's going on. In Go this is sometimes not 100% the case. Also a lot of things are done at runtime, but in Rust you do that at compile time. So you know your types while you build the program. It can never be unsafe at runtime. Same with type expression. So you need to be explicit about your types in C and C++. And you can be explicit or implicit in Go and Rust, which means you can say, let I equals 3, then the compiler knows, okay, I is always an integer, for example. It will infer this type for you in Rust, and that saves a lot of typing. C is sometimes pretty bad at this. It does not support it. Then type checking. There's static and dynamic type checking. For, let's say, a scripting language, everything is dynamically checked. When you execute it, when you run it, when you want to convert it, it will say, is this now working or not? In Rust, for example, this is not the case. You can, let's say, make it static. Everything is type checked statically, and you will always be sure that your types are sound, so that a conversion actually makes sense. In C and C++, you don't have a garbage collector, which is very important for embedded programming, for example. If you have a little microcomputer and you want to run it, well, you cannot use the allocator to put something on the heap, for example, because yeah, there might not be enough time for a real-time CPU to do that. It's just a big overhead. So, for example, also a garbage collector is not nice because the garbage collector can stop the world and clean up all your objects that you might have lying around, and this might break your real-time capabilities. In Rust, you don't have a garbage collector built in. If you want one, you can build one as a library. Let's look at this example here. Speaking of safety. So can somebody spot an error here? Well, I even commented it, but still, you can see that there's 2 pushes on that vector. And the first one can work, but the second one might not, because the vector might have grown already. So you create a new reference, so a new pointer to the first element into your old vector, and it's someplace in memory. And then what we did was we pushed a new element to that vector, but it might have not the capacity to hold both values. So it might grow into some other place in memory. And what can happen is the new place is here, but your old reference is still here. So you have multiple mutable references to the same data. And in Rust, this must be avoided. And you don't need to avoid it, the compiler will. So in Rust, this might not compile. It will not compile. This is the new error message that you will get with the newest nightly build. And what you can see is you have basically the same code. You have a reference, you define it as mutable, you also have a mutable vector here, but if you want to compile it, it will say, okay, here you have a mutable borrow, and here you have a mutable borrow. And the borrow is a very important term in Rust. I will show you the different types of memory usage. So it can guarantee you that there's no segfaults, no data races, no null pointers. To me, it feels a bit like having this guy sitting next to me. Everybody knows this guy? Some nodding faces. I love this guy. So this is John Carmack. He wrote Doom and Quake, and he's one of my superheroes when it comes to programming. And he knows C++, probably he's one of the 10 best C++ programmers in the world. He would say, well, you're freeing it here and you're freeing it there. That doesn't work. Or, ooh, you sure about this? Might be a null pointer, right? So yeah, I have that little John Carmack built into the compiler, and I like that. There's 3 different types of, let's say, data references in Rust. You can have ownership. So you are the owner of your data. And you do that by defining, for example, X as a type. And you say, whatever I want to do with it, I can. I can destroy it. I can, I don't know, shred it. Like your own car. You can do whatever you want with it. Even tune it. Even if it's a Corsa, you can tune that car. You shouldn't. You have total control over it and it's read-write. And then you have mutable borrows, which means you can take it and you can modify it, but it's not yours. It's like a guest book. Somebody gives it to you, you write your name in, you give it back. You're not the owner, you can modify it. And you do that with saying and mute. So you need to be very explicit about this. You need to be explicit on what you want to do with your data. And then there's no locking because it will check at compile time if you break this rule in some place. So, for example, if you have 2 places where you use your variable and they run sequentially, that's totally fine for the compiler. Compiler say, okay, I use it here, but you give it back, and then somebody else uses it, perfectly fine. But if it will see that maybe you have a multi-threaded programming program and they will access the same amount of memory, it will tell you this is not okay. And then you can say, okay, maybe I need a mutex, or I need some other way of locking or a lock-free data structure. But that's up to you then. It will give you some freedom there. But it will definitely tell you when you have more than one access. But it's smart enough to see when it's just sequential and it's fine.
So there will be some runtime
yeah, it's important to have that at compile time. Because at runtime, you can't do anything anymore. You're already doomed. You will have a section. Yeah, that's also a very interesting question. Basically, it will create some kind of flow chart internally, and it will say, that makes sense to me. And it will just look for breaches in those flow charts and say, in the flow graph, you can see there might be a double access here.
So the kind of prediction.
Yeah. And that's very new research from the last 10, 15 years that they built into that language, coming from academics. So this is what you don't get in other languages. You don't get that control flow, static analysis type of stuff at compile time. And then you can have an immutable borrow. You say, you can have many copies of that. So imagine you watch a movie with your friends. Everybody's watching the same movie at the same time, but you're not modifying the movie, you're just watching it. So that's an immutable borrow, and you just remove the mute here, and you get back an immutable borrow. So that was very, let's say, language specific. I'm more of a hands-on type of guy. So maybe you say, okay, I want to write some Rust code. What are the IDEs? What can I use? So there's a Visual Studio. That's not a screenshot of mine. It's running on Windows. It's said to be It has very good Rust support by now. They will work on a lot of integration here. I mainly use this one because it runs on Mac, Visual Studio Code, and recently they released a Rusty Code plugin, and it's very awesome. You can get the slides after the presentation. There's a couple links in there for you to set it up. But it gives you code completion. It will give you a compiler built in and everything highlighting. Pretty awesome. And it's just an extension. But if you are more of an Atom type of guy, also this one is pretty nice. Language Rust plugin at Atom. It will give you mostly the same, also documentation. But what I found was that sometimes the compiler messages are just somewhere and you need to open that thing again and it's kind of messy. So the difference is here I can keep that window open and I see what the compiler is doing. And here I will get some message here at the bar and it's just a bit hacky. There's Cargo. Cargo is a package manager for system programming languages and specifically for Rust. And imagine there's a package manager for this language, and there's no package manager for, at least no standard one, for C++ or C. So how do you know what stuff is out there? And if you share something, how can somebody else integrate it? That's a real problem in the real world. But they did something very right with this tool, because it has everything built in. You can build a tool. You can create documentation for it automatically. You can create a new project. It will set up a Git repository for you. You can run it. You can test your unit tests. You can run benchmark tests, which I will not go into today. You can update the dependencies of your tool. You can search. You can publish, and you can install it even on your local machine. So if you have a cool thing, cool binary that you want to use, you can use that. And here's, if you search for parallel, for example, here's what you get. You get a lot of packages in different versions where people wanted to make it easier for you to run parallel programs. And you can just install that with a simple cargo install, and you get this package. Of course, it's a very young language. So there's some tools that are missing, and there's some tools that work great. So let's go through that list. Unit testing, as I said, is built in. You have a function, and you can write a test with just this test meter tag here. And whatever is written below is just a unit test that will be executed. Very awesome. There's support for unit tests, and there's support for integration tests already built in, and benchmarks. As I said, the package manager supports all that. So it supports build, run, install. Then you have syntax highlighting, as I showed you in many programming languages, in IDEs. Formatting is done by Rust format, which is similar to Go format. It will do the right thing, so you should run it on safe. Code completion is done by Racer. Debugging support is pretty hacky. So there's GDB support, but don't want to talk about it. Clippy is nice for static analysis as a linting tool. You have Cargo Bench for benchmarking. Profiling is also not done yet. There's something like Torch, which looks a bit like this. So it's a tracing profiler, and it will show you how many calls it had for each line. Very useful, for example, here. You might say, OK, I want to optimize this part. And because maybe the square root is a bit expensive to calculate here, we'll tell you. Pretty awesome guy, this Logic. Shout out to this one. Then you have code coverage built into Kcoff. And you can also integrate it with Travis, so you can run it on every build. It's a bit small, but you can see it later on the slides. As a summary, I would say there's a lot of work to do, but it's an impressive start. And this is where you guys come in. We definitely need more Rust programmers in this world, definitely, urgently. Yeah. We need to focus more on building those tools, debugger, profiler, code coverage. There's some links to some very interesting projects. I can click on them later. Like a safe open SQL wrapper, MySQL wrapper. Very, very nice. Or safe OpenGL wrapper. Some bonus links. If you have time, go to the Rust Amsterdam meetup. Never been there, but those guys sound pretty cool. We have a Cologne meetup in Germany. You are very welcome to join. There's the Rust forum. And there's even a huge list of tools that I cannot show in that short time. This is a screenshot of the first link. And it's just huge. It's gigantic. So no time to show that. What I want to do now is some quick Q&A. Yeah. I had one slide prepared that I was too afraid to show, but you asked for it, so you get it. This was a presentation I had yesterday, and a friend of mine said, you can't do it this way, it's too confusing, but I still want to show this slide. So C and Rust, they are good friends. I would even say, this is not Rust, Rustin, maybe, Seaman and Rustin, but I wanted to have it the different way because I would say Rust is more powerful and nobody really likes Robin, but he has the R on it already, so I took it. Foreign function support is very nice. You can remove the standard library, you can replace everything that is built there, and you can just run it from Ruby or Python as an extension, and it will just work. It will not even find out the difference. So that's one of the biggest pros that I did not mention yet. It's a young language, but for example, Mozilla is building a new browser engine called Servo, and it is the fastest rendering engine on the planet. Except for Mozilla, Dropbox is using it to store all your files. So they replaced the... Sorry? I might want to refer you to this list of awesome tools here. Let's just pick one of them. It's tricky to say who's using Rust. You want to know more of a corporate thing or more of libraries that you can use? Nodding? Okay, let's say you're a web developer. Just assume you're a web developer? No. I was expecting this. Okay, then let's do something else. Okay, just assume you're a game developer. You write an OpenGL game, like the next Doom. You can use Glium right now, which is a wrapper around OpenGL without the error checks, because the error checks will be done at compile time. So it will run even faster than C. It will run your OpenGL code faster than C because you can disable those checks. If you read this code, you're blown away, because this is exactly why it's very useful. You get to a lower level even than C. Exactly the same for Diesel. You have an SQL wrapper, and usually if you use an ORM, an object relational mapper, I guess, then you know it might be some overhead. But in Rust, it's not overhead, it's even a performance gain. So the newest version is faster than writing your SQL yourself, because it uses, I don't know, I'm not an expert in that, but some kind of caching for some kind of string caching for the SQL queries statements. And so it's faster than executing that from a normal SQL statement. But look it up, I mean, too much. Doesn't look like it, so cool. Thanks for attending. Try it out, please.